Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to discuss about the module Series Solution of Differential Equations from the paper Mathematical Tools for Materials. So students, let us see what we are going to learn in this module. Firstly, series method of solution, the most general for linear equations, is introduced. First method for series solution near an ordinary point of a differential equation is described. Next, the case of a regular singularity is taken up. First, the case of real distinct roots of the initial equation is described and the convergence of the series solution is established. Then, the case of solution valid for large Z is considered. Next, the case in which the roots of the initial equation are equal or differ by an integer is taken up. Finally, solution of equations with three regular singular points is studied. We begin with the introduction to series solutions of linear equations. We know that many situations lead to linear second-order differential equations. Throughout physics and engineering, we deal with problems related to potential theory, wave motion, heat transfer, and diffusion. These are described in terms of partial differential equation. When simplified, they lead to ordinary second-order linear differential equations. Well-known examples are the Bessel's equation, the Legendre equation, the Airy equation, etc. These equations cannot be solved by any of the analytical methods discussed. Solutions cannot be expressed in terms of rational, trigonometric, or exponential functions. The solution can be expressed in terms of infinite power series. So our aim now in this module is to study the power series method of finding solutions to these equations. We study these equations and their solution in the complex domain. To emphasize this fact, we will take z as our independent variable rather than x. Before we embark on finding a series solution of second-order linear equations, we first wish to see whether an analytic solution to the equation exists or not. So, we consider the equation d2w by dz square plus p of z into dw by dz plus q of z multiplied by w is equal to 0. The functions w of z, p of z and q of z are now complex functions of a complex variable. A point z0 is called an ordinary point of the differential equation if pz and qz are regular in a neighborhood of z0. Otherwise, it is a singular point of the equation. Now we consider some examples. Firstly, consider the Legendre equation given by 1 minus z square times w double prime minus 2z times w prime plus alpha times alpha plus 1w is equal to 0. The equation may be rearranged as follows: w double prime minus 2z w prime divided by 1 minus z square plus alpha into alpha plus 1 into w divided by 1 minus z square is equal to 0. Both p of z is equal to minus of 2z by 1 minus z square and q of z is equal to alpha times alpha plus 1 by 1 minus z square have poles at z is equal to plus minus 1. Hence, z is equal to plus minus 1 are two singular points of the equation and the rest are all ordinary points. For the Bessel equation, z square times w double prime plus z times w prime plus z square minus v square times w is equal to 0. Z is equal to 0 is the only singular point. Now consider next the Aries equation given by w double prime minus z times w prime is equal to 0. In this equation, all points are ordinary and no singular point exists. Next, we move on to find out a solution near an ordinary point. The existence of the solution near an ordinary point is established by the following theorem due to Fuchs. If Z0 is an ordinary point of differential equation given by d2w by dz square plus p of z times dw by dz plus q of z times w is equal to 0, and if a0 and a1 are two arbitrary complex numbers, then there exists a unique function wz that is regular and satisfies the differential equation in a neighborhood of z0. Also, it satisfies the initial conditions given by at z is equal to z0, w is equal to a0, and at z is equal to z0, the first derivative of w is equal to a1. Thus, the only possible singularities of wz are the poles of pz and qz. Without any loss of generality, we take the ordinary point under consideration to be z is equal to 0. Then, since pz and qz are regular in a neighborhood R of the origin, they can be expanded in Taylor series. So, pz will be equal to summation over I is equal to 0 to infinity pi z raised to power I, and qz will be equal to summation over I going from 0 to infinity qi into z raised to power I. We now try to find a power series solution of the equation of the form wz is equal to summation of I going from 0 to infinity ci zi. By substituting these series into the equation and comparing the coefficients of various powers of z, we have minus 2c2 will be equal to p0 c1 plus q0 c0. Similarly, minus 2 times 3c3 will be equal to twice of p0 c2 plus p1 c1 plus q0 c1 plus q1 c0, and so on. The n minus 1th coefficient of z raised to power n minus 1 will be given by minus n minus 1 nan is equal to n minus 1 p0 cn minus 1 plus n minus 2 p1 cn minus 2 plus so on till pn minus 2 times c1 plus q0 cn minus 2 plus q1 times cn minus 3 plus so on till qn minus 2 c0. This is a recurrence relation that determines the coefficient c2, c3 and so on as linear combinations of c0 and c1. We now discuss the convergence of the power series. Here, W0 and W1 are totally arbitrary and can be determined from the initial conditions. So, the computed power series solution given by equation number 2 of the differential equation is formal till we are able to prove the convergence of the series. Thus, let m and n denote the maximum values of modulus of pz and modulus of qz on the circle defined by mod of z is equal to small r. where small r is less than capital R. Then by Cauchy's inequality, we can write modulus of Pn is less than equal to capital M divided by small r raised to power n. Similarly, modulus of Qn will be less than equal to capital N divided by small r raised to power n. Therefore, this implies modulus of Pn is less than equal to k by r raised to power n, and modulus of Qn is less than equal to k by r raised to power n plus 1, k larger of m and nr. Right, now we write modulus of C0 as K0 and modulus of C1 as K1. Then, on using triangle inequality, we have twice of modulus of C2 is less than equal to K1 times modulus of P0 plus K0 times modulus of Q0. This is less than equal to capital K times K1 plus K0 by R. This is less than equal to capital K times 2K1 plus K0 by R, which in turn is less than equal to 2K2, where 2K2 is equal to capital K times 2K1 plus K0 by R. Similarly, 2 into 3 times modulus of C3 is less than equal to 2 into 3 times K3, where 2 into 3 times K3 is equal to capital K times within the brackets 3K2 plus 2K1 by R plus K0 by R squares. Continuing in this fashion, we have modulus of Cn is less than equal to Kn, where n minus 1 times nkn is equal to capital K times within the brackets n into kn minus 1 plus n minus 1 into kn minus 2 divided by r plus so on till k0 divided by r raised to power minus n plus 1. From this, it follows that the coefficients kn satisfy the recurrence relation n minus 1 nkn minus n minus 2 n minus 1 kn minus 1 divided by r is equal to n into kn minus 1 times capital K. This implies small kn divided by small k n minus 1 is equal to n minus 2 divided by nr plus capital K divided by n minus 1, which tends to 1 by r as n tends to infinity. Hence, the radius of convergence of the power series given by summation I going from 0 to infinity ki zi is r, and since modulus of ci is less than equal to ki, it follows that the radius of convergence of the series summation I going from 0 to infinity ci zi cannot be less than r. The coefficients of ci are linear combinations of C0 and C1. Here, C0 and C1 are totally arbitrary, means we have two linearly independent solutions. The general solution is given by Wz is equal to C0 W0z plus C1 W1z, where W0z is the solution of the differential equation that satisfies the initial condition given by at z is equal to 0, W0 is equal to 1, and at z is equal to 0, the first derivative of W0 is equal to 0. Whereas W1z is the solution that satisfies the initial condition given by at z is equal to 0, W1 is equal to 0, and at z is equal to 0, the first derivative of W1 is equal to 1. Every solution of the differential equation is a linear combination of this fundamental set of solutions. As an illustration, we consider an example which represents a simple equation where the result is well known. Let us say the equation is given by w double prime plus w is equal to 0. Here, all points are ordinary points. The solution is known to be in terms of sine and cosine functions. Let us try a series solution of the form w is equal to summation I going from 0 to infinity ci zi. On substituting in the equation above and comparing coefficients of various powers of z, we have summation I going from 0 to infinity I into I minus 1 into ci into z raised to power I minus 2 plus summation I going from 0 to infinity ci zi is equal to 0. On simplifying, we get summation I going from 0 to infinity I plus 2 into I plus 1 into ci plus 2 times z raised to power I plus summation I going from 0 to infinity ci times ci is equal to 0. Now we equate the coefficients of various powers of z to 0 and we obtain I plus 2 times I plus 1 times ci plus 2 plus ci is equal to 0, where I goes from 0, 1, 2 and so on. Ci plus 2 will be given by minus 1 by I plus 2 into I plus 1 multiplied by ci, where I takes the value 0, 1, 2 and so on. Please note that here C0 and C1 are arbitrary. The rest are given in terms of these two by the above recurrence relation. Since the indices in the recurrence relation differ by 2, so we obtain separate relations for even and odd values of the index. This yields the two expressions as C2i plus 2 is equal to minus 1 by 2i plus 2 into 2i plus 1 multiplied by C2i. This is for I greater than equal to 0. The another expression is C2i plus 3 is equal to minus 1 by 2i plus 3 into 2i plus 2 multiplied by C2i plus 1 for I greater than equal to 0. These recurrence relations yield C2i is equal to minus 1 raised to power I into 1 by 2i factorial C0 for I greater than equal to 0. Similarly, C2i plus 1 is equal to minus 1 raised to power I 1 by 2i plus 1 factorial multiplied by C1 for I greater than equal to 0. Thus, the general solution can be written as W of z is equal to C0 times summation I going from 0 to infinity minus 1 raised to power I multiplied by z raised to power 2i by 2i factorial plus C1 times I going from 0 to infinity minus 1 raised to power I z raised to power 2i plus 1 divided by 2i plus 1 factorial. This is simplified to obtain the expression for Wz equal to C0 times cos z plus C1 times sin z. Now we present another example. See, it is not always possible to solve the recurrence relation to get the coefficients explicitly as functions of the index I, but we can calculate as many coefficients as we like. As an example, consider the equation given by w double prime multiplied by within the brackets 1 plus z plus 2z square plus w prime multiplied by within the brackets 1 plus 7z plus 2w is equal to 0. initial conditions are defined as for z is equal to 0, y is equal to 1, and for z is equal to 0, the first derivative of y is equal to 2. The point z is equal to 0 is an ordinary point, so we try a solution of the form wz is equal to summation I going from 0 to infinity ci zi. Substituting in the equation above and comparing the coefficients of various powers of z, we obtain I plus 2 into I plus 1 into ci plus 2 plus I plus 1 square into ci plus 1 plus I plus 2 into 2i plus 1 multiplied by ci is equal to 0. The equation is simplified to find the value of ci plus 2 to be equal to minus of I plus 1 into ci plus 1 divided by I plus 2 minus 2i plus 1 into ci divided by I plus 1. This holds for I greater than equal to 0. From the initial condition, we obtain C0 is equal to 1 and C1 is equal to 2. The recurrence relation then gives the value of C2 to be equal to minus 2 and C3 to be equal to minus 5 by 3 and so on. W is equal to 1 plus 2z minus 2z square minus 5 by 3z cube plus so on. Next we discuss the solution near a regular singularity. Now, a singularity is said to be a regular singularity if the product of z minus z0 and pz and z minus z0 square times qz are not singular at z0, otherwise it is an irregular singularity. In the neighborhood of an irregular singularity, the series method breaks down. Most of the equations that we usually come across have only regular singularities. Let us proceed with some examples now. Consider the legendary equation given by 1 minus z squared times w double prime minus 2z times w prime plus alpha into alpha plus 1 into w is equal to 0. The equation is rearranged. Have w double prime minus 2z w prime divided by 1 minus z square plus alpha into alpha plus 1 w by 1 minus z square equals 0. Here, both pz is equal to minus 2z by 1 minus z square and qz is equal to alpha into alpha plus 1 by 1 minus z square have poles at z is equal to plus minus 1. Hence, z is equal to plus minus 1 are two singular points. However, z minus 1 into pz and z minus 1 whole square have no poles at z is equal to 1. Hence, z is equal to 1 is a regular singular point. Similarly, z is equal to minus 1 is also a regular singular point. Now we consider another example, which is a Bessel's equation given as z square times w double prime plus z times w prime plus z square minus v square times w is equal to 0. The singular point at z is equal to 1 is a regular singular point. Another example is represented by the equation z3 w double prime plus zw prime plus w is equal to 0. The equation has no irregular singularity at z is equal to 0. Now we proceed to study the series solution. As for the case of ordinary point, without any loss of generality, we take the regular singularity to be at z is equal to 0. Then, since z times pz and z square times qz are regular in a neighborhood capital R of the origin, they can be expanded in Taylor series. Z times Pz will be equal to summation over I going from 0 to infinity Pi into Z raised to power I. Z square times Qz will be equal to summation over I going from 0 to infinity Qi times Z raised to power I, where P0, Q0, Q1 are all non-zero. Let us assume a solution of the form Wz is equal to Z raised to power alpha summation over I going from 0 to infinity Ci Z raised to power I. If we substitute these series into the differential equation and compare the coefficients of various powers of z, we obtain the following recurrence relation. C0 times capital F of alpha is equal to 0. Another one is recurrence relation is given by Ci times capital F of alpha plus I is equal to minus of summation over j going from 0 to I minus 1 of Cj multiplied by within the brackets f of alpha plus j times p I minus j plus q I minus j, where I is greater than equal to 1. Consider the equation represented by a function capital F of alpha is equal to alpha into alpha minus 1 plus p naught into alpha plus q naught. Now, this equation is quadratic in alpha and is called the indicial equation. Its roots are called exponents of the regular singularity. Since C0 cannot be 0, therefore alpha must be a root of the indicial equation. Other coefficients are then determined from the recurrence relation. If a function capital F of alpha plus I is equal to 0 for any integer value of I, then the series terminates and we get a solution to the equation in terms of a finite power series. The nature of the roots of the indicial equation is very important. If the two roots are distinct, real or complex that do not differ by an integer, we obtain two linearly independent solutions, one corresponding to each root. If the roots are equal or differ by an integer, we obtain only one formal solution. We next discuss the convergence of the series solution near a regular singularity. Here, we consider the first case where the roots are distinct and do not differ by an integer. If alpha 1 is the root of the indicial equation given by 4, then from equation 3 we have I multiplied by I plus alpha minus alpha 1 times Ci is equal to minus of summation of j going from 0 to I minus 1 Cj multiplied by within the brackets f of alpha plus j p I minus j plus q I minus j. Let gamma is equal to modulus of alpha and delta is equal to modulus of alpha minus alpha 1. Bi is equal to modulus of Ci for I going from 0 to delta. Let m be the least integer greater than delta. Then we have m into m minus delta times modulus of Cm is less than equal to modulus of m multiplied by within the brackets m plus alpha minus alpha 1 times Cm is equal to modulus of summation over j going from 0 to m minus 1 Cj within the brackets alpha plus j multiplied by pm minus j plus qm minus j brackets close is less than equal to summation over j going from 0 to m minus 1 bj within the brackets top plus j multiplied by modulus of pm minus j plus modulus of qm minus j, brackets close. If capital M and capital N denote the maximum values of modulus of z times pz and modulus of z square times qz respectively on the circle given by mod z is equal to small r, which is less than capital R, then from Cauchy's inequality the equation is given by modulus of pi is less than equal to capital M divided by small r raised to power I. Modulus of qi will be less than equal to capital N divided by small r raised to power I. This implies modulus of pi and modulus of qi are both less than equal to capital K divided by r raised to power I, where k is the larger of m and n. Substituting these bounds into equation 5, we get modulus of Cm is less than equal to Bm, where m into m minus delta into Bm is equal to capital K times summation j going from 0 to m minus 1 Bj into top plus j plus 1 divided by r raised to power m minus j. Similarly, we get modulus of Ci is less than equal to Bi for I greater than equal to m, where the product of I into I minus delta and Bi is equal to capital K times summation j going from 0 to I minus 1 Bj into top plus j plus 1 divided by r raised to power I minus j. It follows that Bi satisfy the recurrence relation I into I minus delta times Bi minus I minus 1 I minus 1 minus delta into Bi minus 1 divided by r is equal to capital K times I plus delta into Bi minus 1 divided by r. From this equation, the ratio of Bim by Bi minus 1 comes out to be equal to I minus 1 into I minus 1 minus delta divided by I into I minus delta into r plus capital K times I plus delta divided by I into I minus delta into r. This implies limit I tending to infinity Bi by Bi minus 1 is equal to 1 by r. Hence, the radius of convergence of the power series given by summation I going from 0 to infinity Bi is r, small r, and since modulus Ci is less than equal to Bi, it follows that the radius of convergence of summation I going from 0 to infinity Ci z raised to power I cannot be less than small r. Further, since small r is any number less than capital R, it follows that summation I going from 0 to infinity Wi z raised to power I converges for mod z less than capital R, and the function Wz is equal to summation I going from 0 to infinity Ci z raised to power I is regular for mod z less than r. Let us now find the solution for large z. So far, we have talked of ordinary points or singular points for finite values of the variable z. It is also important to know about the nature of the solution at infinity. The nature of the solution will depend on whether the point at infinity is an ordinary point, a regular singular point, or an irregular singular point. For this study, we make the transformation u is equal to 1 by z and then study the behavior of the resulting equation near u is equal to 0. Making this transformation in differential equation, we obtain d2w by du square plus dw by du multiplied by within the brackets 2 by u minus 1 by u square into p of 1 by u brackets close plus 1 by u raised to power 4 into q of 1 by u into w is equal to 0. The point at infinity is an ordinary point if 2 by u minus 1 by u square into p 1 by u and 1 by 4 q 1 by u are regular at the origin. That is, if 2z minus z square times pz and z raised to power 4 times qz are regular at infinity. The complete solution of the equation in this case will be of the form wz is equal to summation I going from 0 to infinity ci into u raised to power I, which is also equal to summation I going from 0 to infinity ci divided by z raised to power I. The point u is equal to 0 is a regular singular point if u multiplied by within the brackets 2 by u minus 1 by u square p of 1 by u and u square times 1 by u raised to power 4 times q of 1 by u, that is 1 by u into p of 1 by u and 1 by u square into q of 1 by u are regular there. In other words, the point at infinity of the original equation is a regular singular point if z times pz and z square times qz are regular there. The functions pz and qz can now be expanded in Lorentz series given by pz is equal to summation I going from 0 to infinity pi divided by z raised to power I plus 1. Similarly, qz is equal to summation I going from 0 to infinity qi by z raised to power I plus 2. Following the same route as we did for the regular singular point at the origin, we now obtain the following result. If the two roots alpha 1 and alpha 2 of the initial equation alpha square minus p naught minus 1 times alpha plus q naught equals 0 are not equal or do not differ by an integer, the two linearly independent solutions of the differential equation in the neighborhood of infinity are w1 is equal to z raised to power minus alpha 1 times summation I going from 0 to infinity ci into z raised to power minus I. w2 will be z raised to power minus alpha 2 summation I going from 0 to infinity ci into z raised to power minus I. Now consider the case when roots are equal or differ by the integer. Let us find the solution in this case. When the two roots alpha 1 and alpha 2 of the initial equation represented by number 4 are equal or differ by an integer, the method fails to provide two linearly independent roots. If alpha 2 minus alpha 1 is equal to s is 0, then the two roots are identical. If s is an integer, then coefficients in one of the solutions become either infinite or indeterminate after some stage. In either case, we get only one solution. To get the other solution, we take recourse to the method of reduction of order. If w1 of z is the solution corresponding to root alpha 1, let the other root be w of z equals w1 of z into u of z. Then the differential equation is given by d2u by dz square plus du by dz multiplied by within the brackets 2 w1 prime by w1 plus p brackets close is equal to 0. Solve this first order differential equation in du by dz. If we integrate the obtained solution again, we have u of z is equal to a plus b times under the integral sign 1 by 1 w1z square into e raised to power minus of integral pz dz. Since we are interested in the second linearly independent solution only, so we choose a is equal to 0 and b is equal to 1. Hence, the second solution to our differential equation is wz is equal to w1z into uz, which is in turn is equal to w1z into integral under the integral sign 1 divided by w1z square into e raised to power minus integral of pz dz. Let us call the two roots of the initial equation 4 as alpha and alpha minus s. Then use equation number 2 and 2a to obtain p naught is equal to 1 plus s minus 2 alpha. Thus, we obtain 1 by square of w1 of z into e raised to power minus integral of pz dz is equal to 1 by square of the term within the brackets z raised to power alpha 1 into summation I going from 0 to infinity ci into z raised to power I brackets close into e raised to power minus integral of summation I going from 0 to infinity pi z raised to power I minus 1 dz. This is equal to 1 by z to alpha 1 z to 1 by z raised to power 2 alpha 1 into square of the term within the brackets summation I going from 0 to infinity ci into z raised to power I into e raised to power minus of integral 1 plus s minus 2 alpha 1 by z plus summation I going from 1 to infinity pi z raised to power I minus 1 dz. This is equal to z raised to power minus 1 minus s divided by square of the terms summation I going from 0 to infinity ci z raised to power I into e to the power minus integral of summation I going from 1 to infinity pi z raised to power I minus 1 dz. This is equal to z raised to power minus 1 minus s into f of z, where f of z is equal to e to the power minus integral of summation I going from 1 to infinity pi z raised to power I minus 1 dz divided by summation I going square of the term summation I going from 0 to infinity ci z raised to power I. Since c naught is not 0, fz is regular at z is equal to 0. Hence, fz can be expanded in a Taylor series about z is equal to 0, which results in fz is equal to summation I going from 0 to infinity fi into z raised to power I. Substituting these in expression for w of z, we get w of z is equal to w1 of z multiplied by the integral of 1 divided by square of w1 of z into e raised to power minus integral of pz dz is equal to w1 of z multiplied by the integral of z raised to power minus 1 minus s into f of z dz. This gives wz is equal to w1 of z under the integral sign z raised to power minus 1 minus s summation I going from 0 to infinity fi z raised to power I dz. Thus, Wz is equal to W1 of z within the brackets summation I going from 0 to s minus 1 fi z raised to power I minus s divided by I minus s plus fs natural logarithmic of z plus summation over I going from s plus 1 to infinity fi z raised to power I minus s divided by I minus s. In particular, for the case of equal roots, s is equal to 0 and the solution is w of z is equal to f naught times w1 of z into natural log of z plus w1 of z into summation over I going from 1 to infinity fi z raised to power I by I. This results in wz equal to f naught times w1z into natural log of z plus z raised to power alpha plus 1 summation I going from 0 to infinity alpha I z raised to power I. As f naught is not equal to 0, this solution has a logarithmic term and hence a logarithmic branch point. The logarithmic term is present when the exponent difference is non-zero as well, except when fs happens to be 0. Now we consider an equation with three regular singularities. Suppose the differential equation given by w double prime plus pz w prime plus q of zw is equal to 0 has only three singularities at z is equal to z1, z2 and z3. All are regular ones. Now we define capital P of z is equal to z minus 1 into z minus 2 into z minus 3 into small p of z. Capital Q of z is defined as z minus z1 square into z minus z2 square into z minus z3 square into small q of z. These functions are integral functions. Since these are the only singularities, the point at infinity is not a singularity. Hence, 2z minus z square small pz and z raised to power 4 small qz are regular at infinity. This is the case if and only if capital P of z and capital Q of z are quadratic in z and the coefficient of z square in capital P of z is 2. Hence, we can write small p of z is equal to a divided by z minus z1 plus b divided by z minus z2 plus c divided by z minus z2, where a plus b plus c is equal to 2. Qz can be written as 1 by z minus z1 into z minus z2 into z minus z3 multiplied by within the brackets d divided by z minus z1 plus e divided by z minus z2 plus f divided by z minus z3 brackets close. These constants a, b, c and d, e, f are related to the exponents at the three regular singularities. For the regular singularity at z is equal to z1, the initial equation 4 given by f of alpha is equal to alpha into alpha minus 1 plus p naught of alpha plus q naught takes the form f of alpha is equal to alpha into alpha minus 1 plus alpha alpha plus d by z1 minus z2 into z1 minus z3 is equal to 0. If the exponents are alpha 1 alpha 2, then we get alpha 1 plus alpha 2 is equal to 1 minus alpha and alpha 1 into alpha 2 is equal to d by z1 minus z2 into z1 minus z3. Thus, a is equal to 1 minus within the brackets alpha 1 plus alpha 2, d is equal to z1 minus z2 into z1 minus z3 into alpha 1 alpha 2. Similarly, for the other two regular singularities z2 and z3, if the exponents are beta 1, beta 2 and gamma 1, gamma 2 respectively, then we obtain b is equal to 1 minus within the brackets beta 1 plus beta 2. C is equal to 1 minus within the brackets gamma 1 plus gamma 2. E is equal to z2 minus z3 into z2 minus z1 into beta 1 beta 2. F is equal to z3 minus z1 into z3 minus z2 into gamma 1 gamma 2. Since a plus b plus c is equal to 2, hence we obtain alpha 1 plus alpha 2 plus beta 1 plus beta 2 plus gamma 1 plus gamma 2 is equal to 1. On substituting for Pz and Qz into the differential equation and using the above relation, we see that an equation with three regular singularities takes the form w double prime plus w prime multiplied by within the brackets 1 minus brackets alpha 1 plus alpha 2 divided by z minus z1 plus 1 minus within the brackets beta 1 plus beta 2 divided by z minus z2 plus 1 minus within the brackets gamma 1 plus gamma 2 divided by z minus z2 minus w times z1 minus z2 into z2 minus z3 into z3 minus z1 divided by z minus z1 into z minus z2 into z minus z3 multiplied by within the brackets alpha 1 alpha 2 divided by z minus z1 into z2 minus z3 plus beta 1 beta 2 divided by z minus z2 z3 into z3 minus z1 plus gamma 1 gamma 2 divided by z minus z3 into z1 minus z2 brackets close is equal to 0. This may be expressed in Riemann notation as W is equal to P of coefficients z1, z2, z3, alpha 1, beta 1, gamma 1, z, alpha 2, beta 2, gamma 2. Now we consider an example of the associated legendary equation given by 1 minus z square into w double prime minus 2z into w prime plus w times within the brackets n into n minus 1 minus m square divided by 1 minus z square is equal to 0. The equation has three regular singular points at minus 1, infinity and 1 with exponents plus minus half m at z is equal to plus minus 1 and minus n plus 1 at z is equal to infinity. So students, let us now summarize what we have learned in this module. First, in this module, we take up the series method of solving second order linear differential equations. We define ordinary, singular and regular singular points of a differential equation. In this module, we allow complex solutions of a complex variable. We first describe the method near an ordinary point of a differential equation and establish the convergence of the series solution obtained. Next, we take up the case of a regular singularity. We describe first the case of real distinct roots of the initial equation and study the convergence of the series solution which is obtained. Next, the point at infinity is of importance in such cases. The convergence of the series solution valid for large z is discussed. Next, we take up the case in which the roots of the initial equation are equal or differ by an integer. We see that in this case, The solution has a logarithmic singularity in general. Lastly, we briefly study the important case of equations with three regular singular points. Thank you, students, for your patience.